The nuclear force, also known as the force that holds the nucleus together, is a powerful attraction between protons and neutrons, despite the repulsive force caused by the positive charge of protons. The nuclear force is strong enough to overcome it at short range. One interesting property of the nuclear force is that it is attractive in nature, but has a repulsive core. This unique characteristic prevents the collapse of the nucleus and ensures its stability. The range of the nuclear force is extremely short. At a distance of 1 Fermi, which is a minuscule unit of measurement, the force between particles in the nucleus is significantly stronger than the repulsive Coulomb's force. However, beyond a distance of 2.5 Fermi, the nuclear force becomes practically non-existent. Another remarkable aspect of the nuclear force is
that it acts
identically on all nucleons, regardless of whether they are protons or neutrons. Once the Coulomb resistance is taken into account, the nuclear force affects all particles in the same way, at a separation distance of less than 0.7 Fermi. The nuclear force becomes repulsive. This repulsive component determines the size of the nucleus, as the nucleons can only come closer to each other until the force allows. Beyond that point, the repulsive property of the force prevents further closeness. A graph of the potential energy versus separation distance illustrates these properties. From the graph, we can conclude that the nuclear force is a short-range force, and it becomes repulsive when the separation distance is less than 1 Fermi, while it is attractive when the separation distance is greater than 1 Fermi. The nuclear force has significant applications. On a larger scale, it is responsible for the incredible destructive power of nuclear weapons. When a nuclear weapon is detonated, the release of energy is due to the strong nuclear forces at play. Additionally, nuclear power plants utilize the nuclear force to generate heat and produce electricity. In various reactions such as radioactive decay, the burning of the sun, and radiocarbon dating, a weaker nuclear force can transform a neutron into a proton, or a proton into a neutron. These reactions highlight the importance of nuclear forces in different natural processes. Introducing Yukawa's meson theory of nuclear forces. For a long time, the mysterious nature of the strongest short-range forces between nucleons puzzled scientists. However, in 1935, a Japanese scientist named Yukawa stepped forward with a groundbreaking prediction. He proposed the existence of a new particle, now known as the pi meson, which he believed to be responsible for the origin of these nuclear forces. Mesons, the particles in question, come in 3 types: positively charged, negatively charged, and uncharged. The magnitude of charge on a charged meson is equal to the electronic charge. According to Yukawa's theory, every nucleon, whether a proton or a neutron, is surrounded by a cloud of p mesons. The key difference between protons and neutrons lies in the distinct structures of these meson clouds around them. Within this intricate web of mesons, an intriguing phenomenon takes place. There exists a continuous exchange of pi mesons between protons and neutrons. As a pi plus meson jumps from a proton to a neutron, the proton is converted into a neutron, while the opposite occurs when a pi meson jumps from a neutron to a proton. This fascinating exchange process enables the interconversion of protons and neutrons. Moreover, this exchange of pi plus and pi mesons is not limited to protons and neutrons alone. The same principle applies to nuclear forces between two protons and between two neutrons. In these cases, the continuous exchange takes place through pi-zero mesons. The result is the generation of nuclear forces through this exchange process, giving rise to the term
exchange forces.
In summary, Yukawa's meson theory of nuclear forces sheds light on the enigmatic origin of the strongest short-range forces between nucleons. It is the continuous exchange of mesons, specifically pi mesons, that leads to the conversion between protons and neutrons, and the generation of these nuclear forces. This profound discovery not only unravels the mysteries of nuclear forces, but also solidifies the significance of mesons, now recognized as the fundamental agents in this fascinating realm of physics.